Welcome everyone to a new talk virtual seminar on geometry with symmetries. This time I'm very happy to welcome Francesco Pediconi from Firenze, and he'll be speaking about a moment map for twisted Hamiltonian vector fields on locally conformally Kähler manifolds. Thanks, Francesco.
Okay, so first of all, I would like to thank the organizers for giving me the opportunity to speak here. And today I'm gonna report on a joint work that we wrote together with my collaborators, Simone Calamai and Daniel Angella from University of Florence and Cristiano Spotti from Aarhus University, concerning a moment map approach for the action of twisted Hamiltonian vector fields on a class of Hermitian manifolds, which is called locally conformally Kähler. So I cannot okay, it works. Sorry. Okay, so I would like to start by recalling some preliminaries, and in particular some preliminaries about the moment maps. So consider a compact Lie group acting on a symplectic manifold, where symplectic means that it is endowed with a closed true form, which is non-degenerate. Well, if you assume that this action is smooth and effective and that it preserves omega, then by taking derivative of this action, you can you get an embedded at the Lie algebra level of the Lie algebra of G into the infinitesimal automorphism of the symplectic structure. And well, it is actually easy to see that the infinitesimal automorphisms are those complete vector fields X that preserves omega, and this condition is equivalent to ask that the one form obtained by contraction of your vector fields with omega is closed with respect to the exterior differential. Well, if you also assume that your manifold, for example, for simplicity is simply connected, closed form becomes exact. And so for any vector X inside G, you can actually find a potential, so a smooth function X, such that the one form obtaining by contracting X with omega is actually given by the differential of H. And this function, of course, is going to be unique up to a constant, okay? Well, a moment map for the action of G is essentially the dual of the correspondence that takes one vector X inside G and give you the potential X obtained in the way I described it before. So in order to be a bit more precise, well, actually a moment map is going to be, you're going to assume that it is G equivariant, it's going to be smooth and goes from M to the dual of the Lie algebra G, and is going to satisfy a certain equation, so that when you contract M with a vector X and you take the differential, then it's going to be the one form X contraction omega. Okay, this is just like the definition of moment map. Well, actually, this tool, I mean, has a lot of application in symplectic geometry. And the field, the branch of mathematics that study like the geometry of moment maps is called geometric invariant theory. And I mean, one application to that is that it allows you to construct good quotients. So what does it mean, good quotients? Well, in general, if you consider the complexified action of G acting on M, then the topology of the quotient space is gonna be awful. I mean, it's not gonna be a good space, but there's a way to take a good quotient. So, for example, an Hausdorff quotient out of it, and it is by considering the set of points inside the manifolds such that the value of the moment map is 0. So if you consider this set of points, mu minus 1, 0, then there you can consider the action of G, and actually it turns out that the quotient of that this quotient parameterizes the set of closed orbits of the complexified G action. These closed orbits usually are said to be stable. Well, just to give an easy example, maybe the most famous one about moment map and good quotients, we can consider the Lie group C minus the origin, so C star, acting on C2 by means of this action. So you take lambda, a non-zero complex number that acts on a pair xy in this way. So you multiply the first complex number x by lambda and the second complex number y by lambda minus 1. Okay. Well, if you consider the orbits of this action, you're gonna find three types of orbits. The first one is what I in this picture corresponds to the green orbits that are the set x and y such that x times y is equal to t for some non-zero t. These are one-dimensional and closed. Second one of orbits is the origin 0, 0. This is closed and zero-dimensional. While you have another type of orbits that are the axis, so the pairs 0, x comma 0 with x different from 0, and pairs 0 comma y with y different from 0. These last type of orbits, the blue ones, are one-dimensional and they are non-closed. So in particular, they contain the origin in their closure. So the fact that you have non-closed orbits implies in particular that the quotient, that the orbit space of this action on C2 is going to be non-Hausdorff, because you cannot separate points corresponding to the blue orbits with the point corresponding to the red orbits in the quotient. And if you want to obtain a good quotient, well, actually you can, in a sense, you can discard the blue orbits that are the non-closed ones. And actually it turns out that the set of closed orbits is going to be parameterized by the complex number C, right? Well, you can rephrase these last observations that we made in terms of a moment map. Indeed, you can consider the maximal compact subgroup U1 inside C minus the origin. Turns out that the action of U1 preserves the standard symplectic form of C2, and it actually has a moment map given by this expression. So mu of xy is equal to square norm of x minus square norm of y. Well, if you consider the set of points that such that the moment map is 0, well, this is gonna be the union of the two bisectors, okay, x equal y and x equal minus y. And it turns out that this set intersect each closed orbit of C minus origin in a U1 orbit, and the quotient of mu minus 1, 0 with respect to the action of U1 is actually C. So we recover what we were discussing before. Okay, so this was just like a brief introduction to moment maps. Actually, in this talk, we are not really interested in like geometric invariant theory by itself, but rather than we are interested in the usage that we can make of geometric invariant theory in differential geometric problems. So as a general principle, in fact, it has been observed in the past that in some sense the curvature, I'm not being very precise, but the curvature can play the role of a moment map for a certain symmetry group, usually infinite dimensional, underlying a certain differential geometric problem that you are interested in. To mention some examples, well, I think that the first instance where this general principle appeared is due to T and Bott in the 80s, where they were studying Young-Mills equation on Riemann surfaces, and it turns out that the curvature of connections on complex vector Balzons or Riemann surfaces can be interpreted as a moment map with respect to a certain gauge group. Later on, in the 90s, both Donaldson and Fujiki observed that if you're gonna study the CSCK equations on a compact Kähler manifolds, where CSCK stands for constant scalar curvature Kähler. Well, also in this case, this time the scalar curvature can be interpreted as a moment map, and also Jorge Lauret also exhibit the Ricci curvature as or a part of the Ricci curvature as a moment map when studying the Einstein equation on Lie groups and homogeneous spaces. Okay, so it's widely used in the literature, and actually the motivation that stands behind the usage of these moment maps in differential geometry is that, in some sense, it gives you an unified viewpoint of many different problems. And sometimes you can use some tools, some powerful tools coming from GI theory in order to study your geometric problems. And in some cases, I mean, you cannot hope to use directly like theorems from GIT, because sometimes like these moment maps are just formal. For example, when you deal with infinite dimensional symmetry groups. But the point is that this framework can give you some insight into the type of results that you would like to prove, at least. So it gives you like a framework where you can, when you know something, you get some insights. And I mean, it turned out to be really useful, for example, in Kähler geometry. So today we're gonna focus on this second of these examples that I mentioned. So the one due to Donaldson and Fujiki, and we're gonna see how can we extend this framework in the non-Kähler setting. Okay, let me start by recalling some topics about the Donaldson-Fujiki framework. So here, the setting is the following. So fix your favorite compact Kähler manifold, so a triple MJW, omega, not W, where MJ is a complex manifold and W is a Kähler form on this complex manifold, okay? You would like to see the scalar curvature as a moment map for a certain Lie group action, infinite dimensional possibly, on the Kähler class of omega, okay? So here, of course, like the geometry, or once you fix a Kähler class, the geometry is, in a sense, described by a function. So it's natural to expect that the curvature appears as a moment map in terms of a function, so in terms of the scalar curvature, okay? Well, the problem is that if you try with this approach, well, it seems that there's no meaningful way to see an Hamiltonian action directly on the Kähler class. So it seems that there's no symplectic structure on the Kähler class and no Hamiltonian action. So it's not really clear how to construct a moment map picture here. Well, the clever idea behind this is that by means of the so-called Moser's trick, okay, moving inside up to a diffeomorphism, moving inside the Kähler class of omega while keeping J fixed is actually equivalent of fixing the form omega itself and move the complex structure. So actually the Moser's trick tells you that if you take another Kähler metric inside the Kähler class of omega, well, there exists a diffeomorphism that takes one Kähler form to the other one. So by using the pullback by these diffeomorphisms, you can actually change the viewpoint and fix the Kähler form and move in the complex structure. And actually, it turns out that this is the right approach, the right way in order to make an Hamiltonian action appear. And so in order to explain the Donaldson-Fujiki framework, the things you do is you fix your manifold, you fix omega. That's going to be a symplectic form because we want the geometry to be Kähler. And then you work instead of inside the Kähler class, but on the space of compatible complex structure with omega. And I'm gonna be more precise in some minutes. Okay, so the setup here is the following. So you have you fix your compact manifolds, and you can assume that it's connected, and you fix a symplectic form. So as before, it's gonna be the closed and non-degenerate two form on M. Okay, so the natural symmetry group associated to omega is its automorphism group, that are the diffeomorphisms of the manifolds that preserves omega. Well, actually, it turns out that the symplectic structure is a G structure, but it's not elliptic. So its automorphism group is not going to be a proper Lie group. It's not going to be a finite dimensional Lie group. But there's a way that there are some generalization that allows us to talk about infinite dimensional generalized Lie transformation groups on a manifold. I'm not going to be extremely precise about that in this talk because we don't need it, but essentially this can be thought as an infinite dimensional version of a Lie group that has a certain Lie algebra. And the Lie algebra, as we said before, is going to be those vector fields such that the contraction of X with the two forms omega is a closed two forms. Well, in general, I mean the M is not simply connected, so the one form X contraction omega is not gonna be exact. So what you can do is you can consider a distinguished subalgebra of the so-called Hamiltonian vector fields that are those infinitesimal automorphisms of the symplectic structure that admits a potential, so that the contraction X, contraction omega is actually given by the differential of a smooth function X on the manifold. Well, this is a closed Lie algebra of vector fields, and actually it generates another infinite dimensional generalized Lie transformation group. It is called Hamiltonian automorphism of the manifold, and the link between the Lie algebra of Hamiltonian vector fields and the generalized Lie group of Hamiltonian automorphisms is the following. So we say that a diffeomorphism is Hamiltonian if there exists an isotropy with the identity, so that connects the identity of the manifold with your diffeomorphism phi, such that the corresponding time-dependent tangent vector field ZT of the isotropy lies in the Hamiltonian vector fields for any time from 0 to 1. So that's precisely the way you construct a generalized Lie transformation group out of a closed Lie algebra of vector fields on the manifolds, like assuming that this Lie algebra verifies some hypotheses that in this case are fulfilled. Okay, so if we wanna study a moment map framework for this CSCK problem, well, this group, the Hamiltonian automorphism group, is gonna be the gauge group, okay? And he's gonna act on an infinite dimensional space that is the space of compatible complex structure. So let me mention that an almost complex structure on the manifold M is said to be compatible with omega if it satisfies these two hypotheses. So the first one is that omega is type 1-1 with respect to J, okay? And the second one is that whenever you combine omega and J, you obtain a symmetric 2 tensor that we denote by GJ, and we ask that this GJ is positive definite. So it is a Riemannian metric on the manifold. Well, you can, once you have this notion of compatibility, you can construct the space of almost complex structure on M that are compatible with omega, and you can consider the subset of those J that are also integrable. And we denote them, these two spaces, by J almost with respect to omega and J omega, okay? Well, the first remark here is that the first space, the space of almost complex structure that are compatible with respect to omega, can be thought as an infinite dimensional smooth manifold, okay? In particular, they have a natural structure of a smooth ELH manifold, where here ELH stands for inverse limit Hilbert. That is a notion which is similar to the infinite Frechet structure, but it is a bit more it's a bit stronger than being just Frechet. Actually, the subset of those J that are also integrable turns out to be an analytic subset, and this can be easily seen because the integrability of an almost complex structure is actually encoded in the vanishing of its Nanois tensor, and the Nanois tensor depends analytically on J. So this turns out that, so this implies in particular that J omega is an analytic subset of this infinite dimensional manifold. And for any J inside the space J omega, the corresponding Riemannian metric is not only Riemannian, but it's going to be a Kähler metric. Okay, so varying J inside this space of complex structure is in a sense like the same as varying the Riemannian the Kähler metric by keeping its fundamental true form fixed. Okay. Well, this infinite dimensional manifold actually turns out to have a canonical infinite dimensional Kähler structure. And this Kähler structure can be easily described as follows. So actually, first of all, you can describe the tangent space of this infinite dimensional manifold at a distinguished point J, where a point J, I mean an almost complex structure, which is compatible with omega, in this way, so that the tangent vectors is gonna be the endomorphisms of the tangent bundle of M that verifies some properties. In particular, we require them to be skew symmetric with respect to omega and to anticommute with J. Okay. Well, you can construct a triple, bold G, bold J, bold omega in this way. So the complex structure at a point J is tautological. So it's just the multiplication on the left by J itself. Okay, this turned out to be a complex structure. The infinite dimensional Riemannian metric at a point J is just going to be the L2 product induced by the Riemannian metric Gj, and the two form omega, well, is just the two form obtained by combining bold G and bold J. Okay, it is actually just a matter of an exercise to prove that this is indeed a Kähler structure. And as a remark, you can see that the Hamiltonian group associated to omega acts on the space of almost complex structure that are compatible with omega and the action is just given by the pullback. The analytic subset J omega turns out to be invariant under this action, and not only that, but the Kähler structure that we described before is also going to be invariant under this Hamiltonian, under the action of the Hamiltonian group. Well,
Francesco?
Yes?
What if you multiply on the right by J or conjugate by J, that doesn't work, or some property? Or...
If you multiply on the right, I think it's going to be okay. I mean, I should check, but it seems to me that if you multiply on the right, it's going to be okay.
But you get maybe another different Kähler.
Yes, it's possible. I mean, I don't know. I mean, one should check, but I think that right multiplication is okay in some sense. I don't know what happens with the conjugation. I have no feeling about that.
Thanks.
Okay. Okay, so once you have all this machinery, well, you can ask whether you can cook up a moment map for the action of the Hamiltonian group on this infinite dimensional manifold, and actually it turns out that this is possible, and this is a result due to Donaldson and Fujiki. And indeed, they proved that the map that associate to a complex structure J the scalar curvature of the Kähler metric Gj obtained by combining the complex structure with the fixed omega is a smooth map, is equivariant with respect to the action of the Hamiltonian diffeomorphisms, and it verifies differential equations that is a formal moment map equations. It's actually formally the same equation that you saw on maybe the second slides. I don't remember. Okay, so in particular, this equation tells you that if you take the L2 pairing induced by omega of the differential of mu with an Hamiltonian potential h, this up to a certain constant -1/2 turns out to be equal to the contraction of x star with the tautological Kähler form bold omega. Okay, here let me do some comments. I mean, in order to interpret this map as a moment map, we need some identifications. So in particular, we are identifying the Lie algebra of Hamiltonian vector fields with a space of smooth functions. I mean, here to be more precise, I should have said smooth functions up to a constant. Of course, the identification that takes a vector and gives you its potential. And we are also identifying the space of smooth functions and its dual by means of the L2 product induced by the symplectic form omega. Okay. While on the right-hand side of the equation, it appears one vector field x star. Well, actually, x is a vector field of the manifold, is an Hamiltonian vector field, while x star is going to be a vector field on the infinite dimensional manifold of complex structure. That is the vector field that you obtain by differentiating the action of the Hamiltonian group of diffeomorphisms, okay, acting on the left. And I mean, it's if you compute the explicit expression for x star for this vector field, turns out that x star at a point j turns out to be minus the Lie derivative of j with respect to x. I mean, once you have all these gradients, the proof of this equation is just you write down all of these equations. You need to take the linearization of the scalar curvature, and then you get the moment map equation. I mean, actually, this fact turned out to have deep consequences in Kähler geometry. So it's not just a formal equation, but actually gives you some structure. So for example, as I said before, it gives you an unified viewpoint on some different notions. So for example, you can recover the notion of Calabi's extremal Kähler metrics as a critical point of the square norm of mu, and the CSCK metrics as zeros of mu. Well, here, I mean, CSCK metrics in general are not metrics that have zero scalar curvature, but as I said before, mu is uniquely determined up to a constant. So we can actually interpret, in some sense, CSCK metrics as zeros of mu. And not only that, but
Francesco,
yes.
So extremal are precisely the critical points, or
I think so. Yes, are precisely the critical points inside the
because
Kähler class.
the definition, the original definition, are critical points of the square norm of Ricci.
It seems to me that they are equivalent.
Okay, great. No, I'm just asking. So,
it seems to me that they are equivalent.
but originally is this critical point of the square norm of Ricci, right?
Yes, there are several
Thermal?
there are several definitions, right? So
Okay.
it depends on which definition are you using it maybe.
Uh-huh.
But yes, they turned out to be equivalent.
Great. Thanks.
And I mean, and as I was saying before, you cannot really use indirectly GIT techniques here because this is just a formal moment map equation, but turns out that the Hilbert-Mumford criterion, that is a GIT tool, motivates the notion of K stability. That turns out to be very useful in CSCK equations and also the Kähler-Ricci equation, the Kähler-Einstein equation. So you have some deep consequences in Kähler geometry. And I mean, one natural question now is, okay, I mean, this is very good in Kähler geometry, but as we know, not every Hermitian metric is scalar, and not every Hermitian manifold admits scalar metrics. So one can ask, well, if it is possible to generalize this setting to the Hermitian non-Kähler world, so that it means dealing with Hermitian manifolds and J omega, where omega is not closed. Well, like it seemed to us that trying to generalize this setting to the general Hermitian non-Kähler world seems to be out of reach, at least. I mean, I don't know, at least very, very hard. The things we try to do is to restrict to some non-Kähler class of metrics and this Kähler class is precisely given by the locally conformally Kähler manifolds. Well, what is a locally conformally Kähler manifolds? Well, it's just an Hermitian manifold that in general is non-Kähler, but it admits around each point a local conformal change to a local Kähler metric defined on N. So in a sense, this is like the easiest non-Kähler type of metric that you can find in the literature. And we asked ourselves whether we could provide a moment map framework for this class of metrics. And as in the Kähler case, it seems that it is not like appropriate to fix J and move the metrics. So like following Donaldson Fujiki path, what we did is we fixed the corresponding two-form omega, and we worked on the space of some compatible complex structure. So now notice that since we would like to describe some non-Kähler metrics, the two forms omega that we're gonna fix is not symplectic anymore, but rather than is gonna be locally conformally symplectic. So let me say a few words about that. So as before, you fix your compact manifolds, and a two-form omega on M is said to be locally conformally symplectic if it is non-degenerate, as before. And instead of asking that the omega is zero, we ask the following weaker condition. So we ask that for any point of the manifold, there exists a neighborhood of M and a smooth function defined on this neighborhood, so that after the local conformal change, this form turns out to be closed. Okay, this is precisely the meaning of being locally conformally symplectic. Well, there's another way of writing this condition. Indeed, by using the Poincaré lemma, you can you can organize these local conformal changes into a globally defined one form, which is called the Lie form. And being locally conformally symplectic turns out to be equivalent of solving this equation here. So instead of asking d omega being equal 0, we ask that the differential omega is equal to theta wedge omega up to a certain constant that here is going to be 1 over m minus 1, where m is half of the real dimension of the manifold, and that this omega is closed. So this is the definition of locally conformally symplectic and structure, and this is the framework that we're gonna use to work to construct our moment map. Actually, here notice that in some special cases you recover the symplectic framework. So in particular, if theta is identically 0, then omega turns out to be symplectic. So this is precisely a case where omega is closed. And if omega is exact, well, it means that omega has a global potential. And so it means that, no, sorry, I said something wrong. If theta is exact, it means that theta has a global potential. And this precisely means that the two-form omega is globally conformal to a symplectic manifold. And since we are interested in non-Kähler setting, we're gonna assume that this one form theta is not exact. Okay. Well, there's another link with the symplectic word. In fact, if you pass to the universal cover of your locally conformally symplectic manifold, then it turns out that the pullback form, so pi star omega on the universal cover is going to be globally conformal. Of course, the universal cover is simply connected, so it's going to be globally conformally globally conformal to a symplectic form omega hat defined on the total space of the universal cover M hat. And moreover, the deck transformation group gamma of the cover acts on M hat by homotheties. Okay, so it scales the symplectic form. This is actually useful because this gives us a candidate for a good notion of gauge group in this locally conformally symplectic world. So the natural gauge group here acting on the locally conformal symplectic manifold is going to be the so-called twisted Hamiltonian automorphism group. And the twisted Hamiltonian automorphism group is precisely those diffeomorphism of the manifold M that lives through the universal cover and defines an Hamiltonian transformation on the symplectic form omega hat on the universal cover M hat. Okay, so basically the gauge group acting on the base corresponds to the Hamiltonian group of transformations acting on the symplectic cover. Okay, this is an infinite dimensional generalized Lie transformation group, and it is actually possible to characterize its Lie algebra, and its Lie algebra is gonna be given by those vector fields on M that admits a potential, like in the symplectic case. But this time the potential is not gonna be given with respect to the differential D, but with respect to another operator that is called the twisted differential. That is, so the twisted differential d theta is gonna be, it is defined as d minus 1 over m minus 1 theta wedge. And this is precisely the equation that defines the so-called twisted Hamiltonian vector fields on the conformal symplectic manifold M omega. Okay, so I mean we recover something from the symplectic case. Actually, even better, I mean it turned out that in the same way as Donaldson and Fujiki did on the symplectic case, you can construct the space of compatible almost complex structure on M. And I mean, the definition is precisely the same. So it's actually going to be given by those complex structure J that are with respect to which omega is of type 1, and with respect to which the composition with omega gives you a positive definite Riemannian metric. You can define the analytic subset of those almost complex structures that are integrable, and you can also define an infinite dimensional Kähler structure on this space. And actually, it turned out that everything works precisely as in the symplectic case. So here, the observation is that the fact that the omega is equal to 0 or different to 0 plays no role here. So I mean, so everything works precisely as in the Kähler setting, and it is also interesting to notice that the true form capital bold omega on the infinite dimensional manifold is closed. So that's an actual symplectic form on the infinite dimensional manifold, even though the little omega is non-closed. So I mean the framework seems to be good, actually, and one can also show that this infinite dimensional group of twisted Hamiltonian automorphisms acts on the left on the space of compatible almost complex structure by pullback, and that the analytic subset that corresponds to the integrable complex structure is going to be invariant under this action of the twisted Hamiltonian automorphisms. And as before, whenever you vary J inside this space of complex structure, you obtain some Riemannian metrics Gj that are not going to be Kähler this time, but are going to be locally conformally Kähler as we want. Okay, so I mean up to now the framework seems to be promising. So we would like to find an explicit moment map mu for this action of the twisted Hamiltonian diffeomorphism on this infinite dimensional symplectic manifolds given by the complex structure that are compatible with omega. Well, the natural candidate so we saw before, the natural candidate for a moment map is going to be something that relates to the curvature. And again, since in the Kähler case, the moment map turned out to be the scalar curvature, here we expect that the scalar curvature can play, in a sense, the role of our moment map mu. However, since here the setting is non-Kähler, it turned out that it turns out that the Levi-Civita connection does not preserve these complex structures. So we decided to change connection, and instead of looking at the Levi-Civita connection, we consider the chain connection that is a bit more suitable when you want to study non-Kähler setting. Let me briefly,
Francesco,
yes.
There is this new book by Ornea and Verbitsky.
Yes, I know that.
And I think I saw there, I'm not sure, something like the lcK momentum map.
Mm-hmm.
It's a very long book.
I think I know what you're referring to, but their moment map is not infinite dimensional. I think that they consider some action related to the lcK structure, but of a proper Lie group on the manifold M itself.
Okay. So it's a different viewpoint. Okay.
Yes, I mean here this is like the generalization of Donaldson Fujiki framework. So here is like it's a formal moment map on the infinite dimensional manifold. It's a bit different. Yes.
I see. Thanks.
Okay. Okay, so as I was saying, we decided to change connection. So instead of considering the Levi-Civita connections, we use the chain connection. And let me briefly recall what this chain connection is. Is a connection on M defined by combining in a certain way the Levi-Civita connection, the differential of the two form omega and J. With the formula that you can see on the slides. And this is a bit better to study complex geometry in general, because it not only preserves G, but it also preserves J, the complex structure. And it turns out that the chain connection corresponds to the Levi-Civita connection if and only if the omega is 0. So this is like a generalization that coincides with the standard Levi-Civita connection whenever you work with Kähler manifolds. Of course, this connection is going to have a torsion. The torsion of the chain connection has vanishing one part, and it is related to the Lie form of omega, because the Lie form turns out to be the trace of the torsion of the chain connection. And moreover, by tracing the natural curvature tensor you obtain by this connection, you get a function which is in a sort the complex analog of the scalar curvature, and usually one refers to it as the chain scalar curvature of the manifold. So the strategy here is we would like to express a possible moment map in terms of both the scalar curvature of the chain connection and theta that corresponds to traces of the curvature and the torsion. So it seems pretty reasonable, like from a certain viewpoint. Actually, it turned out that there are some problems in doing that. So the first problem that we faced is that this twisted-Hamiltonian gauge group of transformations preserve the conformal class omega, but not omega itself. And this fact implies in particular that your natural candidate for the moment map, that is the chain scalar curvature, is not equivariant with respect to the action of the twisted-Hamiltonian group. And the second problem is also that the twisted-Hamiltonian action does not preserve the infinite dimensional symplectic form. So this seems really bad. I mean, we cannot hope to directly generalize the Donaldson-Fujiki framework. And not only that, I mean, when we also faced another problem, and in particular when we linearized the chain scalar curvature, well, actually we found a term that is the covariant derivative of the Lie form, and it seemed to us that it is not possible to handle this term by using a standard absorption scheme. So, I mean, the natural attempt to prove like the existence of a moment map here would be take the chain scalar curvature and try to add some terms depending on theta or the torsion, whatever, in order to obtain the formal moment map equation. But we weren't able to deal with this additional term given by the covariant derivative of theta. So the idea here to overcome these two problems is to add extra symmetries on your problem or on the framework. The extra symmetries here comes from a certain toral action. So in particular, let me say that the fact that you have this distinguished one form theta on the manifold gives you also a distinguished vector field that is the symplectic dual of theta. Here, noting that even though omega is not symplectic, in order to get the symplectic dual, you just need the omega to be non-degenerate. So it is a well-defined vector field. So you can look at the flow of this vector field, that is a one-parameter family of diffeomorphism on the manifold, and you can actually consider the closure of this flow inside the diffeomorphism group with respect to the standard compact open topology. Okay. Now you need some assumption on this closure. First of all, you need that this closure is compact, so that this turns out to be a true torus acting on the manifold. And second of all, you need that this torus acts by Hamiltonian automorphisms. So let me spend a few words on these assumptions. So the fact that the torus T is compact can be seen as follows. I mean, in general, it is easy to prove that the Lie derivative of omega with respect to the symplectic dual v theta is 0. So whenever you have a complex structure that is invariant under the Lie derivative with respect to v theta, you also get a Riemannian metric with respect to which v theta is killing. So in that case, you can use Mayer-Stirrer theorem to conclude that T is compact. So actually, this is true whenever you get an invariant J, and for example, this is true on the if you start on a Weismann manifold. Okay, so in some cases this is, we know that it is true. The fact that we ask that T is Hamiltonian is due to the following. So the vector field with theta is actually twisted Hamiltonian, and it is easy to show. But the group of Hamiltonian twisted automorphisms, in general, we don't know whether it is closed or not. So in a sense, this is another condition to check. But at least, I mean, it is true if the closure is one-dimensional. So if the closure is just a circle action, the second condition is automatically satisfied. Okay. So once you have this torus action, you focus on the T invariant framework. So what does it mean? It means that instead of considering all the compatible complex structure, you just look at those compatible complex structure that are invariant by the action of the torus. And instead of looking at general twisted Hamiltonian automorphisms, you look at those automorphisms that commute with the action of the torus. And instead of looking at smooth function on the manifold, you look at that smooth functions that are invariant, that are T-invariant. That means that that are constant on the orbits of this torus action. Well, once you focus on the T-invariant framework, things turned out to be much better, because actually the new group of those twisted Hamiltonian automorphisms that comes with T actually preserve not just the conformal class of omega, but omega itself. And so by this fact, it follows that the Chern scalar curvature is equivariant, and the twisted Hamiltonian action preserves the infinite dimensional symplectic form. And concerning the second problem, where the term that we weren't able to deal with turns out to be orthogonal to the tangent space of those complex structures that are also T-invariant. So actually, it cancels. It plays no role in our moment map equation. And by using this observation, we were able to cook up a moment map also in this framework. So this is like the main theorem of the paper I'm referring to, proved, as I said, in collaboration with Angella, Calamai, and Spotti. And we actually were able to prove that under these assumptions, the map that assigns to a T-invariant complex structure J, the scalar curvature of the corresponding the corresponding locally conformally Kähler metric G, plus a certain multiple of the divergence of theta, is smooth, is equivariant, and it verifies a certain equation that can be thought of a formal moment map equation. Okay, this is very similar to what happens in the Kähler case. So let me say that, as in the Kähler case, here you need some identifications, and in particular, you're identifying the space of T-invariant twisted Hamiltonian vector fields with the smooth functions by identifying X with its potential. And we are also identifying the space of smooth functions with its dual by taking the L2 product. And here again, on the right-hand side of the equation, you have a vector field X star on the infinite dimensional manifolds, obtaining as the fundamental vector field associated to X, twisted Hamiltonian. And again, the expression of X star at a point J is nothing but minus the Lie derivative of J in the direction of X. Okay, so I mean, so we obtain this moment map framework in this T invariant, at least locally conformally symplectic framework. Let me say that as an immediate corollary, as we expected, this moment map framework leads to a certain Fujiki type invariant. So this is like a corollary of the previous theorem, and in particular, the value mu bar that is given by the integral, a certain average of the integral of mu j, and the map phi and the map f that assigns to a vector field X the integral of mu j times the Hamiltonian potential of X. Both of these two objects are independent on the complex structure J in the connected components of the infinite dimensional manifolds. I mean, this is just like a formal corollary in the sense that it is like straightforward to observe that the Lie algebra of the torus T is actually, by assumption, lies inside the space of twisted Hamiltonian vector fields. Okay, so actually we can associate to any vector X inside T a vector field on the infinite dimensional manifold, and since the infinite dimensional manifolds are T invariant, the fundamental vector field is gonna be 0. Okay, so like on the right hand side of the moment map equation, you get 0. So it means that on the left hand side you have a certain derivative. So it means that the guy that you have inside the derivative is constant. So which is precisely the content of this corollary. Well, so some final remarks about this. Well, once that we have this moment map framework, we hope at least that this could lead to further notions of canonical Hermitian metrics in the non-Kähler setting that can be thought as a generalization of CSCK and extremal metrics in the setting of lcK geometry, and possibly also on the construction of the corresponding moduli spaces. That is something that in the Kähler case comes from the moment map picture due to Donaldson and Fujiki. The vanishing of the Fujiki type invariant that we found on corollary B can be seen as an obstruction to the existence of T invariant locally conformally Kähler metrics that satisfies the equation that we get via the moment map that we found on theorem A. And yes, another observation is that even though we have a symplectic cover, so that one can ask whether this moment map that we found is nothing but the scalar curvature on the symplectic cover, well, the answer is no. So this object mu that we found is not just something that leads to the scalar curvature on the symplectic cover, but it's something that really encoded some geometry of the lcK or the lcK manifold that you started with. And finally, in the Weismann case, that corresponds simply on those lcK metrics with respect to which the Lie form is parallel with respect to a Leibniz-Beta connection. So in the Weismann case, we want just to recover the constant Chern scalar curvature equation. And I think that's all that I wanted to say today.
Thanks, Francesco.
Thank you.
Are there any questions or comments for the speaker? So, I mean, something, I guess an obvious question is, so one of the most famous applications of all this business in the Kähler setting is, of course, to define the notion of K stability, right?
Yes.
And I mean, what would be the analog problem? So say, do people study the Chern-Einstein question and do you expect that the a notion of stability coming from this framework should be relevant when studying that question?
I mean that would be that would be precisely the reason behind behind this work, like to find a
I
modern map.
see. Okay.
I mean that
Okay, I didn't get. Yeah.
No,
Of
I mean
course.
that. So the answer is this is precisely the aim. So I would say
okay.
so I would say that hopefully we're gonna get some of these characterizations. We are still a bit far from that, in the sense that, for example, like as I said before, in the Kähler case, you have the Moser trick, so that allows you to see like the complexified orbit of this Hamiltonian group as the Kähler form in a certain sense. And here in the lcK setting, we have a version of the Moser lemma, but we still miss like a cohomology interpretation of the complexified orbit. So we are a bit stuck like at some previous level that define our notion of K stability, of course. I mean that. But yes, I mean the aim would be that we study this kind
that's
of
the ultimate goal, so to
yes,
speak. All right.
studying this type of canonical metrics from this perspective, rather than just taking some quantities and saying I want this quantity to be constant or zero. Yep.
Right. Any other questions for Francesco? Well, if it's not the case, then let's thank the speaker again.
Thank you.
Thanks, Francesco. Very nice talk.
Thank you.
Yeah, I mean, maybe one more thing. Let me stop the recording.